Afternoon. Welcome to C3.4 and C3.5. We have some awesome talks for you to enjoy this afternoon. First up, we have Christopher Neugebauer, whom you may recognize as our lightning talk czar. Would you believe it, in his spare time, he actually writes some Python. And today he'll be presenting You Don't Need That, which is a discussion of design patterns and Python.
Oh. Hi, everyone. I wrote these slides in somewhat of a rush after I was stranded in Detroit a couple of months ago. I think they're pretty good, though. Thanks, Jacob. My name is Christopher Neugebauer. I'm going to be talking about design patterns and Python, but not so much design patterns in Python. So I am Australian, but I currently live in Petaluma in California, somewhat north of San Francisco. I also run a small boutique single-track Python conference with Andrew Godwin and a couple other people called North Bay Python. If you're interested in going over to the States at some point in the next few months, come along for our thing, because it's a great excuse. I'm a director at large of the Python Software Foundation as of June this year, and I am currently a senior software engineer at AlphaSites. We connect people who need to know stuff with people who might know that stuff and monetize that somehow. And at AlphaSites, I'm working on a team that's transitioning out of being a Ruby on Rails shop and is moving to a mixture of JVM and Kotlin for infrastructure code and a bit of Python on the side of that. And situations where people are working in multiple languages, it's an increasingly common situation. Development teams are increasingly polyglot organizations, and especially now that we're writing fully fledged UI applications for web browsers, teams might be working on JavaScript for the front end and Python for the back end, or Python for the back end and Java for orchestration stuff or something like that. And there's many different ways that people talk about different programming languages. They might talk about the level of rigidity or flexibility that the language gives you. They might talk about the programming paradigm that they let developers express when they're using that language. But what about Python? Python is a more flexible language than, say, Java, but is a considerably less flexible language than, say, JavaScript. And these days, it has features that make it as descriptive or as flexible as you want it to be. It lets you use object-oriented programming or functional programming features. It can let you express things as functions, or let you express things as classes or as coroutines. And so Python doesn't kind of fit this object-oriented functional sort of paradigm split. And I'd been wondering about how you go about discussing how people write code in Python. And I saw a talk by Luciano Ramalho, who wrote Fluent Python at PyCaribbean this year. And he explained a really great framework to think about how programming languages let you express things. And he talks about languages having features that you can use and not paradigms. And you can think in terms of the feature set that a language gives you. And if you think in terms of that feature set, you can make your programs more expressive by using the feature set of that language to the best of your abilities. And that brings us to the topic of design patterns, which is what I said I'd be talking about today. So let's start with some definitions, because I did high school debating. The definition that I came up with is that design patterns are things that let you express ideas that are hard to express in your language, but in a familiar way. And the vast majority of common design patterns are object-oriented ones, and the most common of those object-oriented design patterns came from the mid-90s. They were sort of put forward by a group known as the Gang of Four, because there were four of them. And they were written, if you know your programming language history, in the mid-90s. Rigid languages like Java and C++ were the state of the art that everybody was sort of moving towards. And so these design patterns that were espoused by the Gang of Four, they tend to fix issues with expressivity that occurs in languages that either are or look a lot like C++ or Java. And so today we are going to write some implementations of some common object-oriented design patterns as if we'd be implementing them in another language, but we're going to use Python because this is a Python conference. And then we're going to look at what features we can use in Python that lets us avoid using those design patterns. And the end result is that we'll end up with some code that makes the best use of the features that Python gives you to write code. And that's hopefully going to help you to come up with ideas on how to port code or ideas to Python without simply transliterating it. But more importantly, understanding why certain design patterns are unnecessary means that you can communicate with developers who use other languages much more effectively, and that might be through writing better Python code and explaining your Python code better, or being able to understand why code that's not written in Python does things in a particular way that may seem clunky or unfamiliar to you. And so to start off with this discussion, I'm going to start with the single, absolute, most simple design pattern there is in object-oriented programming. And that pattern is the singleton. And before I get into this, I need to warn you that the approach I'm going to use is starting with a bad implementation of something, then implementing it more or less well in Python, and then implementing something completely different. And I've had people take photos on the second thing and post them to Twitter, and then I've had arguments about how to implement something that I don't really care to implement. So make sure if you're going to take photos of my slides, take photos of the right slides. I won't tell you which slides are the right slides, so use your judgment. So singletons. Singletons are classes that can only be constructed once. So let's have a look at an implementation of a singleton as you would probably implement it in a language like C++ or Java. So if we were writing Java code in Python, our singleton would look something like this. There would be a definition of the class, which has an attribute that you want to store on that singleton. And then there's an accessor function down here that checks to see if we've got an instance in there. And if it doesn't have that instance, then we go and construct that instance. So this is already really, really complicated code, and it doesn't look like something that somebody would naturally write in Python. We're playing with global variables here. Global variables aren't very cool. There's a value check in that accessor function, and if you've read the Zen of Python, you know that it's easier to ask forgiveness than permission, and that breaks that pattern. So let's see if we can implement this even more Pythonically. So you can. We've got the same class. It's got the same data, but instead of the accessor method, we're explicitly constructing the instance at the module level. So as the module gets executed, we create our instance, and then we delete our constructor method so that future callers can't see that constructor method. Uses features that are in Python to let you do this singleton thing. In languages like Java, you'd use a private constructor that can only be called once. And then you access the data from the instance just as you would any other way. And you also can't call that constructor. So going del on the class object does actually prevent other people from being able to call it. So that's cool. So you can implement singletons in Python just fine. You can implement it as if it's Java code, as if it's C++ code if you're not thinking about how to use Python. Or you can implement it in a way that looks Pythonic without existence tests, without accessor methods. But instead of doing that, you might want to stop and ask yourself a question. Why would you do something like this? And to answer that, you need to answer a different question, which is what exactly are you actually trying to achieve with the code that you're writing? And so if you go look through the Gang of Four, you'll see why people who are using languages like C++ or Java need singletons. And the first reason is that in pure OO languages like Java in particular, where everything has to be inside a class, you get namespacing from singletons. You can put all of the related data and related functions into the same class and make that a singleton. But Python already has pretty good namespacing functionality. You don't need to create classes to get namespaces. The other reason why singletons are useful is so that you can pass functionality around to other functions. A singleton might be a derived class of a base class or an interface. So say you have two singletons that have the same interface. So we've got one singleton called spam, which has some data on it, and the other singleton is called eggs, which has some data on it. So they've got the same interface as far as Python is concerned. You can pass them into a function because they've got the same interface, and you won't get errors and stuff like that. So here's the two things we need. We need firstly to prevent multiple construction of our namespacey thingy, and we also need to be able to pass our object as arguments to a function. And it turns out that Python already has a feature that lets you pass these, that lets you do these two things. That feature is Python's built-in modules system. And let's look at why this works. First up, in Python, everything, or almost everything, is a variable. And by almost, I mean that anything that holds data or holds functionality is a variable. And what this means for you is that class instances and modules look more or less like exactly the same sort of thing once you start passing them around to consumers. So instead of defining classes to hold all your data, you can define a series of modules that have the same attributes in them, and you can pass them around as if they were the same instances as you had before. And as you probably already know by now, Python's import mechanism makes sure that you always end up with the same object when you import a module, no matter how many times you import it and no matter where you import it from. And so you get this interpreter level enforcement of single construction, regardless of what you do with that object, which is cool. So it does both of the things that we want. And so in summary, you don't need to go and implement things as singletons in Python because the module infrastructure in Python does that for you. And it does it for you in a way that's more expressible and more familiar to even beginner Python programmers. You don't need to explain to them all these features that prevent you from constructing something more than once because they see modules when they start coding, basically. And so following on the same line, we're going to look at a technique called dependency injection. Dependency injection is particularly popular in Java land to the point that there are giant frameworks that do this thing for you. It's exceedingly popular. And the basic idea is that you provide dependencies to classes as you construct those classes, rather than the classes going and finding the dependencies as they need to use them. Ironically, these dependencies often turn out to be singletons, in case you want a clue as to where this section of the talk is going. Okay. So the best way to illustrate this is by working in reverse. Say you want to create mailer objects that retain a sender address, and so you can send lots and lots of emails from that same address. So here we construct our mailer object, and we have this send method down here, which calls out the send mail function that we've imported from somewhere like that. This is a contrived thing that might look okay in Django if you squint really, really hard. So the version with dependency injection kind of looks different. Rather than importing send mail, we pass in an object at construction time, which is this mail sender thing. That's the dependency that we are injecting. And then we call the method on the object that the dependency that we injected. So this version is strongly object-oriented. It basically comes as a necessity based on how Java worked historically. If we're going to implement this in a way that looked good in Python, it would probably look like this. We pass in a function at construction time and then call this stored function. It's not nearly as Pythonic as importing the function you want and then calling it directly, though. To remind you, that's what importing the function looks like, in case you don't know what that looks like. Okay, so why would you write it the first way? People who write Java code for a living could write their code exactly like this. Import the function that they want and call it directly. But Java coders don't do this. So let's talk about why you would want to write things with dependency injection. Testing. And specifically unit testing. That's testing where you separate out all the individual parts of your code and test them individually against known data and known dependency behaviors. So unfortunately, most people don't write code that is amenable to easy unit testing. Instead, they write code that relies heavily upon dependencies. And so when you have dependencies that are embedded within your code, you need to use mocks to get rid of those dependencies. Mocks are pretend versions of functions or objects that provide known fixed behavior for you to reason about and test. And most object-oriented languages have mocking frameworks. The mocking framework in Python, however, is actually very, very different to how mocking frameworks in, say, Java work. And the reason for this is that in Python, basically every variable everywhere, including those variables that are in the standard library or places like that, they're all writable. And because every module, function, and object is a variable in Python, that means that you can write to any module, function, or variable or object. So instead of writing a mock like this and passing it into our object at construction time, instead we can override the dependency with our mock function like this and test that behavior instead. I've written code that does exactly this thing. I don't particularly recommend it. Instead, there are frameworks that can do that overriding for you and do it in a way that is tractable and understandable. And it's right there in the standard library in unittest.mock. And so unittest.mock has a patch function. It allows you to patch any namespace object with a mock object, and you can ask questions of that mock object at the end of your test. And patch will undo any changes that you might make once you leave that scope. So in summary, Python doesn't need dependency injection because you can override any objects or functions that you need to override at test time. So I promised in the abstract that I'd talk about threads. Who came here to hear me talk about threads? I'm sorry, I'm not going to talk about threads. Go check out async IO instead. So the next thing that we are going to talk about is something in a slightly different direction. I'm going to talk about iterators. The iterator pattern is something that lets you iterate over custom collection types. You may be familiar with them. Here's a really bad implementation of Python's range object. It's got a constructor. It takes up to 3 arguments. And it has an iter function that returns a range iterator. And then range iterator looks something like this. It has a constructor that sets the initial current value of the iterator, and it has a next function that returns the next item in the range, or raises stop iteration if there's no next item. I've also added this has next function down the bottom because this is what Java's iterator pattern expects. It's also going to make the next slide a bit easier to read. And so you can iterate over this iterator with a while loop if you wanted to do so. Or you could write it like this if you're going to use the Python primitives. Use the built-in iter function and look for stop iteration yourself. And naturally, this while loop doesn't look particularly Pythonic. And that's because this iterator pattern is actually one that's described by Python as being an officially supported thing. Python provides you with a tool to consume iterator objects built into the language, and that feature is the for loop. The looping construct takes care of calling iter for you, it takes care of calling next, and takes care of looking for stop iteration for you. And so you might think to yourself, but Chris, is this not an officially supported Python pattern? And I would say yes. But once again, I ask you this question: what are you trying to achieve? Would you like to write an iterator like that yourself? Managing an iterator is actually not that easy because you have to think about what's happening inside a loop, completely outside of the context of the loop itself. So you have to think about what's happening here while your consumer is thinking about what's happening over here. And so the solution to that is generators. And generators are like functions, but they handle packing this state away for when you aren't using them. If you're going to talk... Okay. Generators are like functions that handle packing away state for you when you aren't using them. So instead, you can write an iterator in terms of loops. It's much simpler to write, and you get to think about the same sort of programming construct in your iterator code as the place that's going to use your iterator code. And in the case of Python, I write my own iterators a lot more frequently than I do in languages like Java or C++, because it's much, much easier to write my own iterators in Python now that there's a language construct for it. So you don't need these explicit iterators because generators actually make it easier. And so we're going to run with that idea, taking, using generators in Python to render other design patterns obsolete. And the pattern I'm going to look at is the visitor pattern. And the idea of the visitor pattern is that you easily perform common operations on all the elements of a collection. And you do this by passing an operation object to that collection, and the collection goes off to find all the elements of it and tells the operation which elements to perform the operation on. Basically, it has the concept of acceptors and visitors. Acceptors are your collections, and visitors are the operations that you want to perform on each of the items inside your collection. So I've got a generic tree-like data structure here. I'm using a very generic sort of tree because I didn't want to write, I didn't want to have too much complication here, but this could be anything you want to traverse. It could be like a directory structure in your file system or a JSON object or something like that. It has data at each point in the tree, and it has some children. And so if we're implementing the visitor pattern, we have a method that accepts a visitor operation. We've called it accept here. And that visitor operation makes sure that every element gets visited by the visitor, sort of by going down the left side and then looking at the current item and then going down the right-hand side of it. And a visitor will look like this. It has a method that accepts an item, and it has a way to perform an operation on it. And so we can look at this again, and we can wonder what we're trying to achieve. And as with all design patterns, it exists because something wasn't easy to do in another language. So let's think about what it's actually trying to achieve and then write some code that does it in a way that actually looks good. So in this case, what we want to do is we want to separate the structure of a collection from the operation that we're trying to perform. And as I said before, not every language makes iteration easy. The visitor pattern came about before most object-oriented languages had built-in first-class support for iterators. It was much easier for classes themselves to know what their own structure looked like and handle calling operations themselves, rather than trusting an outside caller to know how to handle the order of iteration correctly. But as we discovered previously, Python not only supports first-class iterators, it actually makes it easy to do that. And so instead of writing a visitor acceptor pattern, you just make it easy to get at each element of your collection in turn using an iterator. And then you can perform your operation inside a for loop. And this is kind of great because people who write Python know that for loops indicate that you're going to do something on each element of a collection. So this actually signals to people who know what Python looks like that we're doing something across multiple items of a collection, which is not something that the visitor pattern does natively. So in this case, iterators separate the structure of the collection from the operation that you want to perform on the elements, and it uses signals within the code to tell the reader exactly what is going on, and you don't have to worry about the whole encapsulation of classes, which is actually something that Python makes quite difficult to do, at least compared with Java. And so if you need to have multiple different iteration methods, depending on the order in which you traverse down things, it's not hard to write multiple generators because writing generators is easy. And so Python doesn't need visitors because generators separate the structure from operations, and that's what the visitor pattern does. And so that's 4 design patterns that don't actually make all that much sense in Python because there are features in Python that let you do that. Here are some bonus slides for you that I wrote after the last time I gave this talk, because I wanted to point out that there are some venerable design patterns, even from the Gang of 4 book, that not only work in Python, but are actually the right thing to do. So let's look at the factory pattern. Factories are callables that can create instances of an object that fulfills a certain interface. So here's a URL reader factory. It's a static method on a class. It looks at some parameter, and returns the right sort of thing that you can read from based on the sort of URL that you pass in. This is a really flimsy implementation of URL opener and URL-lib. And so factories exist in Python because constructors in base classes have to return an instance of that particular base class. They can't return instances of subclasses. And this is a limitation in Python. It's a limitation in basically every object-oriented language there is. But you might be wondering, why is there a static method here and whole object and all those sorts of things? So let's look at how we construct things in Python. When you construct things in Java, for example, you have to go, like you want to construct an object, you go new that object. But in Python, well, we've got the open built in, which opens a file. And the second is the string IO object. And looking at this as a consumer, you can see that they look like exactly the same sort of thing. You can't tell which is a function, you can't tell which is a constructor of a class. You don't have to say, I want new string IO. I say, just give me a string IO. So construction uses the same callable patterns as functions. And so rather than creating a whole class to serve as your factory, you just use functions instead of creating factory classes. The logic is exactly the same, you just call it in a different way. And so it turns out that factories are used all through the Python standard library. The socket constructor is a factory function, URL openers tend to use factories, the open function built in is a factory. They're used everywhere because they're still useful in Python. And Brandon Rhodes is writing a book on Pythonic design patterns that include a bunch of design patterns that are actually useful in Python and make use of Python's features. The factory pattern is one of the patterns he introduces, but there's many, many more of them. So that brings us to the end of our tour of Python features. So you've probably realized by now that a lot of object-oriented patterns look quite clumsy in Python, and hopefully you've kind of got an idea of why this is the case. So first up, a lot of design patterns exist because there are features in Python that don't exist in other languages. You should strive to use those features that you have access to rather than re-implementing those patterns in Python. Secondly, some patterns exist because more rigid languages have binding restrictions that prevent you from overriding names or passing around functions. Generators replace a lot of patterns that describe control flow and let you convert complicated ideas around state or iteration into much more familiar constructs. And in summary, basically, when you are writing Python, write code like you're writing Python. Thank you very much.
Right.
It looks like I have a couple of minutes for questions, so if you've got one, put your hand up and a mic will find you.
Thanks. I've inherited some code which was written by a Java programmer, and not being familiar with Java design patterns, I don't necessarily recognize what constructs there are. Have you got a hint for how I can look at that code and think, okay, right, this is this particular design pattern, and here's how to unpack it and make it more Pythonic?
Read the Gang of Four book, but read the Gang of Four book in a critical way so that you can think about what things they're talking about can be replaced with things that exist in Python. There was someone over there. Were you interested? Yeah.
Hey, how you going? Thanks for the talk. We use factories all the time in every project I've ever worked on, factories all over the place. But you isolated the reason we do that. And the reason you gave was that when you call the init, you always get back the class that you were constructing, or not a subclass. But in Python, we don't need to. We've got done the new, which allows us to return a different class type than the class type that we're calling the constructor on. Is it maybe that I just started thinking maybe that's the way we should be implementing factories?
So I think people have an expectation when they're writing Python that things will behave in certain ways when they do certain familiar things. And overriding new so that it has vastly different semantics to what people expect is a way to make your code very difficult to read. Creating a factory function is something that's understandable by most people, I think, whereas doing, like, overriding new so that the behavior of new is different to what people expect will mean you'll have to explain how your code works to more people. I'm always in favor of writing code that is understandable and easy for other people to read, often because I will come back to it myself and forget how I did things. And the simpler code I can invariably understand, and the complicated code I can't.
Thank you.
Because I'm not particularly good at remembering what I do.
Your comment might have been a throwaway comment, but it's inspired me. I'm going to go away and write a decorator so that we can do it neatly.
Okay. Any other questions?
I think that's all we have time for today.
Great. Okay.
But thank you so much for your talk, Christopher.
Thank you.
I certainly learned a lot.